Okay, this is the title of my talk, Tailored Integral Operator, Green's Function-Based Fixed-Point Iteration Methods for Numerical Solutions of Boundary Value Problems. Okay, I need to give you the rationale behind this talk. Usually, you know, whenever we have OTHA conferences and so on, these seminars are published on YouTube, you know. So I encourage my students and colleagues to take a look at them, you know. Many say, oh, please, guys, can you make it more general, you know? You know, it's too specific. Like I used to, in my previous talk, I used to talk about Navier-Stokes equations and fluid dynamics and so on. So I said, okay, this time I will try to make it very general talk, but I hope not to make it boring to the audience in here, you know. So let me tell you what's the rationale behind my talk. These days, it's very tough to have like undergraduate students in measuring in mathematics, you know. And even if they measure in mathematics, the vast majority, they want to go to the applied math track, you know, not pure math track, 90%. This is, you know, maybe North American institution, this is the case. Probably in Russia, it's very similar. Applied mathematics tracks like mathematical biology, let's say financial mathematics, actuarial mathematics, but the majority of them, they do numerical methods of solutions. And these days we have this hot topic, which is data science, as you well know. But the problem, as they go through numerical methods, they find out, you know, they figure out that without solid theoretical background, it's very difficult to do applied mathematics and numerical mathematics. Okay, so the idea behind my talk is I'm going to share with you, for the past several years, I worked with many students measuring in mathematics. I supervised the senior projects and master's thesis, many, okay? And I found that, of course, numerical methods, most of them, some of them worked fluid dynamics, but the majority worked numerical methods. But I found fixed point iterations numerical methods, although they are not great numerical methods, but they are really so accessible to undergraduate and master students. I'm not talking about PhD students. First of all, very accessible to them. And second, they can learn a lot from these iterative methods. First, they can do some modeling. They need a background in, let's say, differential equations. They need a background in fixed point theory. They have to show convergence of the method, okay? And also they have to implement it, you know. So they have to do some programming, you know. But these days, you know, they can use computer algebra systems such as Maple or MATLAB, you know. But it's a long, you know, learning experience, several things they have to learn. But the problem, as they learn all of this, they find out that many questions arise more than solve, you know, so they solve the problem, but many theoretical questions arise. So they realize that without solid mathematical background in pure mathematics, it's hard to do applied mathematics, you know. So I'm going to share with you what most of them worked with me and how many questions came up with this. Okay. Okay, so I will do problem statement. I will show you the iterative methods, overview Green's function, fixed point iteration method. This is from fixed point theory. Method description, of course, we have to do convergence and numerical results. And at the very end, okay, it will not be general talk. I will tell you what currently our work is on these days. You know, it's more specialized in. Okay, so you have this linear operator, L of y, N of y is nonlinear, and f is a function, you know. Okay, and this differential equation is, of course, supplemented with initial or boundary conditions. Here is an example of such a class. I took fractional boundary value problem, alpha derivative, alpha between 1 and 2, so it's kind of second order with two boundary conditions, you know. Okay. All right. Let's take a look at this nth order differential equation where you have here the non-homogeneous term. Okay, I'm going to introduce the gamma function, the Green's function. Basically, the Green's function says, the method says, if you replace f of t with the delta direct function, then you can solve the differential equation. Delta function is 0 everywhere except at one point it blows up. So it's close of solving the homogeneous equation, but it's slightly more than homogeneous. So the Green's function is the solution of this differential equation where f of t is replaced by the delta function. Okay, so this differential equation, of course, has supplemented with boundary conditions and of them. So what's the Green's function? It satisfies, this is the linear operator L. So L, G is delta. So the solution where this is delta is called the Green's function, you know. So if we solve it with the non-homogeneous terms replaced with the delta function, then we can represent the particular solution in terms of the Green's function. Okay, now how to construct the Green's function, you know. So, you know, the delta function is 0 everywhere. So before t less than s, it is 0, so homogeneous. So we're talking about n linearly independent solution for the homogeneous. And after t bigger than s, it is homogeneous. So we have here, before s, it is linearly independent solutions, and linearly, and after this, n linearly independent solution. Okay, so we have two unknowns. To solve them, we need two n equations. So the boundary conditions are n, so we're left with n equations. By the way, I should stress that we require that the Green's function satisfies the corresponding homogeneous equation. So if you have u of 0 is 3, so the Green's function is 0, you know, satisfies the corresponding homogeneous boundary conditions. Okay, so we have n boundary conditions, so we need n more. So the function has to be continuous, first derivative continuous, second derivative continuous. So here, it satisfies the boundary conditions, n of them. First derivative continuous, no, the function is continuous, first derivative continuous, and up to n minus 2 derivative continuous, you know. So we have here n minus equations, you know. We need one more equation, you know. Now you have Gn is delta function. So Gn minus 1 derivative is the delta function. So which function has derivative delta function? In the generalized sense, it's the unit step function. So the last condition, as you see, it's the right side minus the left side equals the jump, you know. This is the coefficient of the highest derivative, you know, of the differential equation. If it is 1, then the jump is 1. So here we have n equations, so we can, with the n boundary conditions, so we can construct the Green's function. Okay, just a quick look, you know. This is the Caputo fractional derivative in case I give examples. And this is the Laplace transform of the derivative. Just you have this extra term, you know. Okay. All right, so this is a quick overview of Green's functions, how to construct it. Let's do it for this fractional boundary value problem. We can do Laplace transform. So what's the Green's function? We replace f by delta function, you know. And notice the boundary condition I told you, replace a and b by 0, you know. It satisfies the corresponding homogeneous boundary conditions. So we can do just Laplace transform, I showed you, some computation, and we get this is the Green's function, you know. This is the unit step function. And here is the Green's function for this one. You know, the Green's function is important for also proving existence of differential equations. Okay. Let's take this fractional boundary value problem. We have minus lambda squared y of t, same. So we replace f of t with the delta function with the corresponding homogeneous condition. We can apply Laplace transform, and maybe you'd like to take a look at the Green's function. It's expressed in terms of EAB, which is the Mittag-Leffler function. This is the Green's function. By the way, one of my students, you know, computed the previous one for the case alpha equals 2, and it simplifies to hyperbolic function. The Mittag-Leffler function simplifies to the hyperbolic function. Okay, here is the Green's function. Oh, the previous ones were boundary conditions, but I wanted to give you one with initial conditions. Sorry, this is A, B, this is C. Sorry, I just noticed the misprint. So we can construct the Green's function. So replace the F with delta, and here the homogeneous initial conditions. Here is the Green's function. Here, as you see, it is what now? One piece. Here it's 0 on the other side. So please keep this one in mind, because I need to make a remark on this. So I'm sure you know all of this. Okay, but I want to show you what the idea we came with Green's function. Okay, then we move to another topic in math, which is fixed point theory. We have these very famous iteration methods to find fixed point for a function. So this is Picard. This is the iteration. You start with y of 0, apply t to it, you get y1. So to find fixed point schemes, they are called, very famous in fixed point theory. We have this one, Krasnoselski's iteration. We have parameter alpha here, gamma. So it's more general than this one. If gamma is 1, it reduces to Picard. I'm picking some of them, the most famous ones. And we have Mann's iteration. Okay, Mann's is like the previous one, but as you see, the alpha is a sequence, not one parameter. At each step, you have an alpha. And this very famous one, which we did lots of work, it's Ishikawa. It's kind of implicit, 2 steps. Okay, so what's the idea? So we have the Green's function. We have something in another area of math called fixed point theorem, right? We try to combine both of them. How? Okay, so let's take this fractional boundary value problem. Oh, by the way, I told you, if you find the Green's function where the non-homogeneous terms is replaced with delta, this is the particular solution. It's expressed in terms of the Green's function. By the way, there should be some terms here outside, some terms, but this is the expression for particular solution if you have homogeneous boundary conditions. But usually, let me make this important remark. So usually you get more terms outside if it is non-homogeneous, you see. But what I will do, I will not bother about this term, because when I do the iterative scheme, you have to start with y0, right? I will choose y0 to be this term, this. So I will choose y0 when I construct the iterative scheme. I will choose this to be the terms outside. Okay. So here is the method. Let's define this integral operator. Okay. Okay. I subtracted f, added f, rewrite it in another way. Yeah, just reorder it. We notice that this one is a particular solution. So this is you can rewrite this operator in this way. So what do you do with this operator? The idea is, why not have operators and embed them in fixed point iteration method? So we embedded this operator in Picard's iteration. So L is an integral operator. So this is the idea. So we embed them. Look what we got. We got this iterative scheme, Okay, we got this iterative scheme. We came up with Picard Green's iterative scheme. Okay, now my students usually do this one on Maple, because Maple, I think, it's more friendly than MATLAB and so on. Basically, they need some background in numerical integration, and there are many methods out there. Simpson's rule, trapezoidal rule. Composite trapezoidal rule, many, so they have to implement it and see what's this one. Okay, this operator that we defined earlier, you can embed them in other iterative schemes other than Picard. Okay, let's embed them in Mann's procedure. If you remember Mann's, it has a sequence, right? So here is Mann's. By the way, beta n, at each step you have beta n. So look what happens, this is the iterative scheme. Let me go back and show you the difference between Picard's and Mann. This is Picard's. Man is the same, except this constant pop out here outside the integral. Okay? So easy to implement it. You need to do, I told you how to choose the initial iterate. It's the terms outside, I showed you before, the extra terms outside the integral. And of course, you can face some numerical integration difficulty and so on. Oh, now, sorry. Now, okay, see the students run these and so on, then, they enjoy this kind of work, but we face lots of problems. What's the problem, What's the value of beta n that gives you the fastest rate of conversion, which is we call optimal beta? First of all, if you, the problem is you have too many betas here. So it's better to have one that balances all. Because if you want at each step to find beta 1, beta 2, numerically it's headache, and error accumulates. So okay, now what the student can do, like they do a program, trial and error, they can best find the optimal beta that gives you the fastest rate of convergence. But the problem, how do you do it theoretically? How can you compute it theoretically? This is one of the open questions we have. And unfortunately, so far, I don't have students to work on this one. What's the optimal value of beta theoretically? Okay, now this is not an easy question because I'll give you an example. In numerical methods, we have iterative method for solving linear system of equations. It's a SOR method. You know the SOR, successive over relaxation method. Right? There is also an alpha there, or beta. And there are many theories that gives you the optimal value of beta. For example, one theory says that if the linear system, the coefficient matrix is triangular, if it is triangular, and if it is positive definite, then the optimal value is expressed in terms of the spectral radius and some complicated equation. But it's lots of theorems there, It's very complicated. So now we don't know theoretically how to find the best beta. Another problem, So this one, numerically, we can do it. Another way we can do it just in a simple way, which is accessible to students, what we did is, you see the residual error? You know what's the residual error? If you have this equation, L of u plus N of u equals F, the residual error is this minus F. You can minimize the L2 norm of the residual error. So here, we can do minimize the L2 norm of the residual error. Okay. Another question we have, so how do you do this theoretically? Till now, we're stuck on it. Another question is, some differential equations, the iterative scheme converges very fast, sometimes medium, sometimes very slow. So what is the rate of convergence of the method? So this is like theoretically, there are lots of work in fixed point theory talking about the rate of convergence of the method. And this is an open, yeah.
You have T, G depends on T. What is T?
Oh, sorry, very good question. The differential equation should be y double prime of t, for example. Okay, because when you integrate with the x here from 0 to 1, x will disappear and you have the solution as a function of t. The differential equation is in terms of t, the solution, like cosine t. X will disappear.
Okay.
Okay, so I showed you before that G, right? So if you like to take a look at one of the boundary conditions, I replaced G by its value, and this is the iterative scheme for Mann's iteration. Okay, if you like to look at Ishikawa, here is the iterative scheme. For the students, it's a headache to implement this one on Maple. It's very tedious. I will not do it, so they help with this one. Oh, by the way, Ishikawa, the problem I should mention, you have two parameters, alpha n, beta n. Theoretically, there is hardly any work. What's the best alpha n, beta n that gives you the fastest rate of convergence? It depends, of course, on the nature of differential equations, on the coefficients, on the order, and so on. Another question. You have a boundary value problem. Ishikawa works. Mans doesn't work. Picard doesn't work. Why? We don't know why. Okay? Sometimes you apply Ishikawa, because Ishikawa, Picards and Mann are special case of Ishikawa. Sometimes Picard works. So given a class of differential equation, how can you tell theoretically which one will work? So hardly any work on this one. So as you see, lots of open questions. Oh yeah, here we can minimize. We can minimize the L2 norm in terms of for Ishikawa alpha and beta, and we have two parameters here. It's more difficult. Of course, for the students, they have to show convergence of the method. And this is one of the theorem. They use the contraction principle, Banach Picard fixed point theorem for this one. Here is the Ishikawa for this. And I can show you one theorem. Here is one theorem. Assume that the function f, which appears in the definition of the operator Tg, is such that if this condition is less than 1, then Tg is a contraction, and hence Ishikawa iteration converges strongly to the fixed point iteration. You have to have some convergence theory. Okay, all right. Now, just let me check the time. Okay. Now, when we were doing this work, it was brought to our attention that in calculus of variation, there are also iterative methods, right? But there, it's called, oh, here. This is calculus of variation. We found, we don't do work in calculus of variation, but we found that they have iterative methods from A to X, where lambda t is the so-called Lagrange multiplier. After some work, we figured out that lambda of t, this Lagrange multiplier, is actually the Green's function. And we have one publication, short publication in Applied Mathematical Letters. We showed that they call it Lagrange, but it's basically the Green's function. Okay, given that this is the Green's function, so we said in another paper, why they take from A to X? As I showed you, the Green's function is two pieces unless you have initial conditions. So if you have boundary conditions, actually, it shouldn't be A to X. There should be another term. So we showed in another paper is that this in calculus of variation, you should have A to X lambda 1 Lagrange multiplier plus x to 1 2 Lagrange multiplier, because the Green's function is two pieces actually. So we improved this idea in calculus of variation. So look at this connection, how it happened, just by luck. Okay, so here we said the setting should be like this in calculus of variation. There should be another piece. Okay, so of course we implemented on differential equations. If you like to take a look at this second order, differential nonlinear M can be anything more than 1. Okay, which shows y0, 1 plus t. Y of 0 satisfies the corresponding homogeneous terms with the given boundary conditions with these, because the Green's function satisfies the homogeneous ones. And this is Ishikawa for this problem, 2 steps. And what's the best alpha and beta n? The students did minimize the L2 norm and look at the alpha they got and beta, the best one that converges. Of course, they checked it numerically by trial and error. They say it matches with this one. And look, for this problem, I showed you, Ishikawa gave the best results. Picard was slow and Mann was slow. Why theoretically this is the case? It's till now it's ongoing work. Lots of questions. And sometimes these Picards don't work, nor don't converge. Only Ishikawa works. Oh, this is the graph of the L2 norm of the residual error. Okay, you see the minimum minimum, this is alpha, beta, and this is the best one. The minimum is the best one that gives you the fastest rate of convergence. Okay, now people publish lots of numerical work, and this is, they say, it's a very great method and so on. But honestly, numerical work, if you want to be pragmatic, they don't work always. So I'm going to show you that this iterative method, if you have this very famous Strach's problem, they're not going to work. What's this Strach's problem? This is the test bed for boundary layer problem. And so I will end up with this example, and I will show you what's the work. Why these? So iterative methods, even, okay, so they will not work on this one. What's this Strach's problem? It's a boundary layer problem. I cannot recall what's the graph, but let's assume it's like this. This is one. Then, yeah, this is one. So you see, we have a boundary layer here. If you want to do numerical work, let's assume you have to have a mesh here. Equal distance mesh, regular mesh. You will not catch the boundary layer. It's very thin. It can be 10 to the power minus 10. So you can't catch this piece. There is no way. So this iterative method, even other finite element collocation method, they will not work on boundary layer problem. This is a boundary layer problem, and the layer on the other side, on the right side here. Okay, so these methods we cannot do. So the only way you can go around it, you have to have an idea about the nature of the boundary layer. This, when it blows up, it's like tangent hyperbolic. So what we did some transformation, variable transformation, tangent hyperbolic, and the problem converted to this one. Now the Green's function corresponds to the linear term here. The linear term, you have y double prime, and where is the linear term? There is, yeah, we have this lambda squared y. So move them. So you have to find the Green's function for the linear term. Okay, and of course the boundary conditions are different. So only after we transferred it and like swallowed the boundary layer, then you can able to do it. But with boundary layer problem, numerical methods very difficult to do. So with this is the Green's function, and after we did the transformation, we were able to solve it. This one, Picard worked for this one. Here is some error. Oh, yeah, by the way, this one, as you notice, we have lambda here. And the bigger the eigenvalue, the narrower the boundary layer, very low. But it works always, Just, I will finish in 1 minute. Yeah, this is, we compared with B-spline, Galerkin method, variation. Look at the Strach's problem. Here is how it looks like. Look how thin the boundary layer here. Very, very thin, 10 to the power minus 12. The bigger the eigenvalue, the smaller the thickness of the boundary layer. Okay, so I gave you an example just to be realistic. These iterative methods, not big deal, but students can learn a lot out of them. Okay, but our current work now is on boundary layer problem. My current work, they are different than other numerical methods because numerical methods usually you come up with a method and you prove convergence. Boundary layer problems, no, they don't work this way. You have to have the boundary layer, have an idea where is the layer, left, right, or the middle, and you have to have an idea about the thickness of the boundary layer. Then you can come up with a numerical method and show convergence. Our work is the most famous researchers on this is Gregory Shishkin. And Shishkin is a Russian mathematician. So we're doing his work now, but we're generalizing it to fractional boundary layer problems, which hardly anyone is working on fractional boundary layer problems. Okay. Okay, here is Shishkin. Actually, it's some papers in his second doctoral degrees. his most of the work on Shishkin. Anyway, some publication we have, and I shouldn't forget the last one, which is thank you.